Good morning and welcome to a wonderful Wednesday, everyone. I am so tickled to see everyone in class today. It's nice to hear your chatty energy as you socialize in person for the first time in what seems like just like months and months of like Sundays. It feels like every day's been Sunday for the last little while. Just like always anticipating going back. Any case, today we have two exciting topics. Arithmetic and geometric series are very interesting math topics, and we're going to apply them to finance tomorrow. But let's start with some financial applications. Simple and compound interest. Okay. So, what are we talking about with simple and compound interest? Let's take a look. Simple interest is earned only on your deposit. So your initial deposit here, in this case $1,000, was being doubled every year, but the doubling doesn't double itself. It only affects the initial investment, the 1,000. Okay, and the formulas that we can use for that are over here. Why is it going on here? Why is this not working? Oh, it's not working, Mr. Jennings, because it helps you plug your technology in. Okay, there we go. Learning something every day. Distance learning, everyone's learning. Okay, so when we want to calculate how much interest am I going to earn, then all you need to take a look at, so I is interest, and the amount of interest that you're going to earn is PRT. Well, what are those things? P, this number means the principal. And principal is the amount that you deposit into your investment. R is your rate of return, so that's your interest rate. And T is time. So the amount that you will have is given by this formula. Amount is A, and that's equal to your principal plus the amount of interest you've earned. And these create lines. They're very straightforward. Okay? So let's take a look. If we borrow $2,300 at 7.5% annually and earning simple interest, how much would we have to pay back in 10 years? So someone is going to borrow money, perhaps toward their business or something. Every year they pay 7.5% on the principal only. How much will they pay back over that time? So this would be what we would take a look at is here our amount is equal to the principal plus the interest. So we can write that also the amount is equal to 2,300 plus, well, what's the interest? PRT. Okay. What are R and T? R here is 7.5%. So we could write that as 0.075. And T is 10 years. Nice, simple numbers. T is equal to 10. Okay, so now let's substitute those values in here. A is equal to 2,300 plus 2,300. Notice you could factor that. You could factor 2,300 out of this. I'm not going to right now. Multiplied by 0.075 multiplied by 10. Okay. And now let's evaluate. Now this we can just plug and chug on a calculator. 0.075 times 10 would just be 0.75. So it would be 3/4 of 23. And then we would have A is equal to, well, let's just punch it. Boop. Open up your calculator. Boop. And then we have 2,300 plus 2,300 times 0.075, that's the rate, times 10 equals $4,025. Very straightforward. 4,025. Okay, circle it. That's final answer. Therefore, he will have to pay back. This is David. Okay, so David will have to pay back $4,025. Just like that. Now, let's keep going. Joshua, he's borrowing $1,000 from his friend, but he pays back $1,050 after 6 months. And we want to find out what was the simple annual interest rate that he paid. Okay? So clearly he paid $50 in interest. All right. So we have here A is equal to principal plus interest, and I'm just going to write interest as P times R times T. Okay. What is R? That's what we're trying to find. So we want to know what rate did he pay his friend. T was given to us as 6 months. So what should I put in there for T? Should I put in 6? He says, clearly hoping that a forest of arms shoot up into the air saying, no, Mr. Jennings, that's clearly the wrong answer. Why would I not put in 6 here? Yeah. Thanks, that's perfect. 0.5, that's half of a year, so let's put in 0.5. Okay, so now the amount that he has to pay back, that's known actually, so let's not write in A again. Amount is here, so we'll write it in. 1050 is equal to 1,000 plus 1,000 multiplied by R, which is unknown, multiplied by T, which is 1/2. Okay, evaluate. So I can do this multiplication, and I can also do some inverse operations here while I'm writing another line of subtracting 1,000 from each side. Okay, subtract 1,000 from each side. That's going to help me isolate R. R is the desired unknown, and it's hidden behind layers of armor. This is the first layer we'll peel back. And so that, you'll notice, isolates over here the amount of interest he pays, which is $50. And then that's equal to 1,000 times a half. Well, 1,000 times a half is 500. And then that's multiplied by R. So now we can very easily find R by one more inverse operation dividing by its multiplication. So it's being multiplied by 500, so let's divide both sides by 500. Then we get 50 over 500, which is... What's 50 over 500 as a percent? 10%, yeah. So this would be 0.1. 0.1 as a percent is 10%. So R, therefore, R is equal to 10% interest. So he was paying 10% simple interest. There are lines. We've been studying lines since grade 9. Compound interest, on the other hand, is much more interesting. We've introduced exponentials in this year, and exponential functions have that trait of having a very interesting curve that does exciting things over a human frame of time, the human time frame. So let's take a look. This looks a lot, the amount in the formula, the amount looks a lot like an exponential function, where we've looked at exponential functions before. F of x is equal to some initial value multiplied by the growth factor, call it a d, raised to the power x. Okay? So here we have the growth factor, which is 1 plus the interest rate, which you'll recall is the same way where we were building our growth factors in the past. And it's raised to the power n, where n is the amount of time. But I is doing something funky here, and we need to understand where these two numbers, I and n, come from and what they're doing. And to talk about them and what this C is, let's go down to the next page. So when we're talking about interest rates, here I didn't tell you how often interest is compounded, but we assumed it was every year. But interest can actually be applied to an investment at different times throughout the year, a different number of times, that is to say. So if we're applying the interest in one shot at the end of each year, if you had $100 in your bank account, and then at the end of the year they apply interest of 10%, it would be 110. There's the other option. C is 1, and we don't worry about it, because numbers like 1, when we're multiplying them or dividing them, we don't care. We don't write those down. But when we're applying interest twice a year, what that's going to do, and I'm just going to write those formulas here, I is the interest rate earned per compounding period. And it's equal to the interest rate per year as R divided by the number of compounding periods. And then the number of compounding periods is equal to, and that's N, and that's equal to the time in years multiplied by C. So for example, we're going to take 10% here. Yeah, let's do 10%. That's fine. We could do 12% as well. Now let's do 12%. 12% is going to give us nicer numbers. If we look at 12% interest, well, what I and what N is that going to produce with the semi-annually? Well, here I would be equal to 12 divided by 2, and that would be equal to 0.06. This is 12%. 0.06. And the N, well, that would be T times C. So if it was 1 year, and we could say 12%, let's look at 5 years. N would be T times C, so that would be 2 times 5, so N would be 10. Okay, and I would be 0.06. If we were to take a look at what about if we apply interest 4 times a year? So that could be on the equinoxes and the solstices, the height of winter, the height of summer, and the middle of spring and fall. So here, if C is 4, then our I would be 12 divided by 4, so that would be 0.03. And our N, well, that would be 4 times 5, so that would be N is 20. So it just shifts the growth factor and the exponent that we're raising things to. If we were to apply interest monthly, you would earn 1% per month, because 12 divided by 12 is 1, so it's 0.01. And N would be 12 times 5. N would be 60. And let's have another color here. Let's do the last one. Here, if you were to apply interest daily, that means you're applying fractions of a percent every day. Then your interest rate that you would use here would be equal to 12 divided by 365. So you're going to earn, they're going to spread this 12% and give you a little piece of it every day. And then your N would be 5 times 365. That's just how you're going to use those to get those numbers. Claire? I chose it. It's 12% interest. Are you saying, where can I get 12% interest, Mr. Jennings? Sign me up, please, because I've already seen that 1% does some pretty cool things. Can't wait to see what 12% does. Then you're right. 12% is a great interest rate that you might earn if your stock portfolio was doing well. Yeah. So if you can find some fancy investments to get that kind of money return, that's great. Your money is performing very, very well at 12%. What is N? N is the number of compounding periods. And so we get N by taking the amount of time in years and multiplying it by the number of times we compound per year. And I is the amount of interest earned per compounding period. Whenever we hear that word per, we know division is involved, and this is how you find I. So let's take a look at some examples. So if we are compounding continuously, sorry, this is not an example, but in Delta Math, you're going to be asked, what about if you compound continuously? What that means is every instant, your money is earning tiny fractions of a fraction of a percent. So rather than waiting to the end of the day to compound, it compounds every second, but not only every second, but every instant. And then this formula here will give you that. This is the first time in your math career that you've probably seen the number E. Anyone know this number E? No. It's a constant like pi. It's a real number, and it's a real fancy number. It is 2.718, blah, 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 blah. If you use 2.72, that would be a pretty good approximation for our purposes.
At this point, like the y value on the exponent, the e of x,
yeah,
isn't it like the same value of the e
of its slope
on the thing is the same as the slope, and it's the same as the
yep.
area.
And the same as the area underneath. Yeah, it's its own derivative and it's its own integral. It's very cool. But for now, just know that if you compound continuously, you don't get infinite money. It doesn't work quite that way, but it does go towards this number 2.7. It approaches that number as you compound continuously. So let's take a look. If we were to deposit $10,000 into a saving account that compounds interest quarterly, so here, let's take a look. This is our P. This is our principal. This is what we invest initially. And then we compound interest quarterly. All right. So this tells us that our number of compounding periods per year is 4, because quarterly, 4 times per year, at a rate of 8% per year. So here is R, is 8%. And then how much will you have after 5 years? This is T. Okay. But we need the numbers I and n if we're going to approach this problem. And I is equal to the rate divided by C. So here our rate is 8% and our C is 4. So let's just write those in here. 8%, but we're going to apply that quarterly. So that's going to be 2% per quarter, writing that as a decimal, 0.02. This is our I. Okay, we need that number. N is time multiplied by C. Here, time is 5 years and C is 4. So we will get 20 compounding periods over the life of this investment. All right. So let's take a look. We're going to put this in our formula. The amount of money that we're going to have is equal to the principal multiplied by the growth factor, which is 1 plus the I, 1 plus the interest rate, 1.02. This is 2% every 3 months. And we're going to raise that to the power n. So that's 20. So here. So just writing our formulas out over top so you can see where these numbers come from. The amount we're going to have here is equal to the principal multiplied by 1 plus I, all raised to the power n. And now, substituting in, we will have their $10,000. And then this is something that we can evaluate. We could do that on a calculator. How much money will we have after this 5-year investment? So we go over here, we say 10,000, please. I'm going to invest $10,000. I'm going to raise that to the power, multiply that by 1.02, but that is raised to the power 20. So here, this number is how much money we will have after that amount of time. 5 years, and we've almost increased our money by 50%. So that's pretty cool. 14,859. So the amount that we're going to have is equal to 14,859 point, I think it was 47, was it? Yeah, 47. Cool. 47. So that's pretty cool. Over 5 years at a reasonable interest rate, 8% is something you can achieve. You can find investments that will give you that. Not savings accounts, but you also don't need to be breaking kneecaps to get that. You can make $5,000 by otherwise doing nothing and just not using $10,000 for that amount of time. But how much would you need to invest now? Okay, so now, if we know that we're going to be investing for 10 years with an 8% interest rate, but now we're compounding monthly, how much would we need to invest now in order to get this? Okay, so this is what we will have. So this is A. This is the amount we want. How much do you need to invest? This is P, and we don't know it. So we want to know how much to invest now to get this in 10 years. Here is our T for time. Here is our R for rate. And here is our C. Our C is compounded monthly, so that's 12. So let's find I. I is equal to 8%, which is the rate, divided by the compounding frequency. N is equal to T times C. So T times C is 10 times 12 is 120. Okay. Now this would reduce. This is 0.08 divided by 12. And so the factors 4 come out. And so that would be 2 over 3. So it's 2/3. 2/3 of a percent every month. And so I could write that as 0.006667. If I want to round that to 4 kind of significant decimal places. See? Oh, compounded monthly. Yeah. So also, Mr. Jennings, there's a lot of formulas you're throwing at us. Where can I find them? Oh, you can find them over here. So if you're looking in here, and you look at our doc, they are on today for Wednesday here. So there we are, Tuesday. Here are our Wednesday. Simple and compound interest. Compounding periods is there. And then our formulas for simple and compound interest are there. Okay. And just learning to use the formulas today. So now let's put it into our formula, which is A is equal to P multiplied by 1 plus I raised to the power n. And we can substitute into here and then isolate P. So let's go ahead and we'll substitute all of these values in. So we know A. We know that we want to have 20 grand in 10 years. And we know that we can get an 8% interest rate that's compounded monthly. So that's, we don't know P, so just write down P. 1.006667 or so. Now, you could use a decimal approximation. You could use a fraction, no problem. All raised to the power of 120. Okay. Now, I can evaluate this and then divide by it and move it over, or I can divide by it now and punch it in on my calculator. And I prefer to do the latter. So I am going to do some inverse operations here. Because I know my goal is to find out P, that's what I want to find. How much do I need to invest right now? And so to do that, I'm going to isolate right away before I punch it. 1.006667 raised to the power of 120. And I'm going to divide that on both sides. To the 120. And then this, of course, this will cancel that because it's the same. So it just isolates P. And then this is what I can punch on my calculator to calculate P. So let's do that. I like to go to my calculator once. I don't like to do my calculator, write down a number, and then push that number into my calculator, punch another button. I like to do all of my algebra on paper and then just do the last punching on the calculator whenever possible. So I know that I want $20,000 divided by, and I'm going to put it in brackets, 1.006667 raised to the power 120, and bracket, and then I say, and so that is the growth factor that I would get at 8% compounded monthly for 10 years. I'm going to be more than doubling my money. So when I divide the amount of money that I want by that, it will tell me that you need to invest now 9 grand. 9 grand and $10 and a dime and a penny. Basically 9 grand. Yeah. So therefore, P is equal to $9,010.11.
Wait, what did you just do between the division and getting like the original?
Pushed equals.
Oh.
Yeah. When I wrote in 120 like that, and then I close the bracket, it tells me this is the value of your denominator, and then when I push equals, it evaluates the whole expression. So yeah, it took me a while to make friends with my calculator, but now I gather all kinds of useful information from this computer calculator. I quite like it. We're friends now. Now, what would be the difference if I invest 10 grand for 10 years at a 10% interest rate, if I compound annually or I compound continuously? Okay, this is just going to allow you to compare. If we compound continuously, that's the most frequently we can compound. If we compound annually, that's the least frequently we can compound. Let's see what the difference is so that we are developing our intuition for these numbers. And that's why I chose really simple numbers for these examples. So if we were to, we're going to gather our numbers. This is P, this is T, and this is R. Our C, in one case, is going to be 1. So I'm not going to really worry about that. But then when it's continuous, then we use a whole different formula if we're compounding continuously. So if we're compounding continuously, our formula is A is equal to P multiplied by the constant E multiplied by R raised to the, E raised to the power RT. Sorry, it's R times T. It's very cool. E to the R to the T. E to the R times T. Okay? So you can think of it as PERT, but you have to remember E raised to the power RT. Okay? Over here, with compounded annually, well, we just use our standard formula. A is equal to the principal multiplied by 1 plus the interest raised to the power n. But in this case, n is t because our c is 1. So we would take t, multiply it by 1, and that will give us 10. So let's sub in over here. The amount that we would have if we compound annually is going to be 10 grand multiplied by 1.1 because we're getting 10%. So this is 110% there. 1 plus 10%. Raised to the power 10. And that we can evaluate. Over here, on the other hand, we will have the amount that we're going to have, and it's going to be a different A. So maybe I'll call that A2 for compounding continuously, and this A1 for compounding annually. and this is going to be equal to still 10 grand, still same initial investment, multiplied by E raised to the R times T. Well, R is 10%, so that's 0.1, and T is 10 years, so that's 10. What's 10 times 0.1? 1. 10 times the 10th is 1. So these are like, you can think of numbers as sets of instructions, right? If I'm multiplying by 10, that's a set of instructions that says whatever your number is, let's say I'm multiplying 88 times 10, it says take the number 88 and move the decimal place 1 over, means add a 0. If instead I'm multiplying by 0.1, 0.1, then that's a set of instructions saying move the decimal place the other direction. In these cases, they cancel out and make 1. It's also like saying 10 times 1 over 10. Well, the 10's cancel. It's just 1. So T times R is 1. So I'm going to be raising E to the power 1. Basically just the number E. Okay. So E would be our growth rate over 10 years at 10%. We're just going to be multiplying our money by E. Pretty cool. So let's take a look at what these do in the calculator. So I'm going to go over here. Going to clear out my calculator. Going to take 10 grand. And I'm going to do this one first. Times 1.1 raised to the power 10 equals, and there it is. That's how much money we would have there. Nearly 26 grand. So there, our A would be 25,937. Going to round to the nearest dollar. And let's compare that with this here. Well, we already know the number E, but let's just do it on our calculator just to prove it to ourselves. Here's the number E. It's already on my calculator. So I push E and I multiply that by 10 grand. $10,000, the easy thing about that is it's a set of instructions saying move the decimal place 4 times. So let's do that. There is the number E with the decimal place moved 4 times. So we can see this is 27,183. And this shows you compounding continuously, because you're earning your interest and then immediately earning more interest on that interest, it does do better. It's not that big a difference though. It's less than $2,000 difference on your money over 10 years compared to compounding annually. So if we wanted to know how much more money we would have if we invest compounding continuously rather than annually, we would take this number and subtract this number, 25,937. So let's do that. Minus 25,937 to get, well, $1,246. $1,246. So therefore, you would be $1,246 richer if you got continuous compounding rather than compounding annually. Okay. So as we're shifting those numbers between I and R and T, N, and C, as those numbers shift up into the exponent, things do perform a little bit better, but not all that much so. The biggest factor is basically that interest rate is much more important. Okay, so these are all the topics that we have for simple and compound interest. This is the idea that links time and money in our society, is that money now is more valuable than money later. Because you can use it now. Everyone would prefer to have $1,000 in their pocket than $1,000 in 10 years. But that relationship of money later, because we can exploit interest and grow our money, it does change the equation for us over our lifetimes. And when you are young, your time is a powerful ally if you want to grow your money. If you can start investing sooner, it is better. So pick up that extra shift at Blue Mountain this weekend.